We have all been there. You check your phone, it says clear skies, so you leave the umbrella at home. 10 minutes later, you are caught in a torrential downpour. Why can meteorologists sometimes nail the forecast down to the minute, while other days they completely miss the mark? The atmosphere is full of random, unpredictable fluctuations. Statisticians call this natural chaos noise, and it is the exact reason forecasting is so difficult. To make sense of this, meteorologists rely on standard deviation. Standard deviation is a mathematical tool that measures exactly how spread out a set of data points is from the average. Figuring out that spread is the mandatory first step. Once you can measure how much the data fluctuates, you actually have a shot at predicting the unpredictable. This animated chart shows how that works in practice. On the left, we have a low standard deviation, meaning daily temperatures stay tightly clustered around the average, making for a highly predictable month. On the right, the line spikes wildly up and down. That high standard deviation indicates chaotic, unpredictable swings. This metric applies far beyond the weather. Real estate agents use standard deviation to measure housing prices, helping buyers understand whether a neighborhood's market is stable or prone to massive price jumps. Human resource managers use the exact same math to analyze salaries across a company. By measuring the variance in pay for a specific role, they can spot wage gaps and ensure employees are compensated equitably. Standard deviation serves as a universal measuring stick. It gives us a concrete number to assign to uncertainty. Businesses rely on historical data all the time to try and predict what their customers will do next, navigating directly through that real-world unpredictability. But this creates a serious dilemma. If a company runs a new ad campaign, or a hospital tests a new medication, and their success metrics go up, how do they know the intervention actually caused the spike? Because the world is noisy, that sudden bump in sales could simply be a random, lucky coincidence. To solve this, researchers use a concept called hypothesis testing. They start with the null hypothesis, which is the baseline assumption that any result you see happened purely by random chance, and your intervention had zero effect. Good statisticians have to act like extreme skeptics. By assuming their success is just a fluke right out of the gate, they force themselves to mathematically prove that their results are real. The specific tool they use to interrogate the data and disprove the null hypothesis is called the p-value. The p-value, or probability value, calculates the exact mathematical likelihood that the results you are looking at occurred entirely by accident. To make a firm decision, researchers set a strict threshold called the significance level, or alpha. In most fields, this alpha level is locked in at 0.05, or 5%. Looking at this bell curve, the outer red zones represent that 5% threshold. The golden rule is that if your calculated p-value lands in this critical region, meaning it is lower than 0.05, your result is officially deemed statistically significant. A low p-value provides hard mathematical proof that an effect is genuine, completely eliminating luck as a suspect. So how do we actually calculate that p-value from a pile of raw data to prove significance? We generally rely on two primary formulas to test our data: the z-test and the t-test. Use the z-test for 30 or more observations when the population standard deviation is known. It maps data to the standard bell curve shown here. For samples under 30 with unknown deviation, use the t-test. Its wider curve accounts for small sample uncertainty, making it robust. Choosing the correct test for your dataset ensures your resulting p-value is mathematically valid and trustworthy. When you step back and look at the broader implications, these tools do a lot of heavy lifting in our lives. We often picture statistics purely academically, a professor at a chalkboard calculating the odds of rolling dice or flipping coins. But it's the exact same math, allowing meteorologists to predict severe storms, marketers to verify ad campaigns, and scientists to validate life-saving cures. Statistics is a lens filtering out the random chaos of the world, allowing us to find genuine, provable truth hidden right there in the noise.